All right, so my last video cut off early, which is good because I actually was starting to make a mistake down here. I didn't realize it in time. I actually ended up finishing the problem. So I'm just going to go over what I did from where that video cut off. What we had done is we had verified that the critical number that we found, 2r over 3, 2 little r over 3, I should say, is in fact going to give us a relative maximum. And so we wanted to take that value and plug it back into our volume function to determine what that maximum volume is. I used the wrong function down here, which is why I scribbled that out. Proceeding up here, we're evaluating v. Remember, v is this function for volume at big R equals 2 little r over 3. And what I'm doing is I'm using this form of the function, where I made a substitution for big H right there. So plugging in 2r over 3, that would give me pi. And then big R squared is going to look like 2 little r over 3 quantity squared times H over R times R minus big R, which again is 2r minus 3. What you're seeing from here in these next couple of steps is just simplifying all of that down. What you end up with is 4 pi r squared H over 27. Okay, and it should not be a surprise that little r and little h are making an appearance here. Remember, those are constants. Obviously, you know, the values that you choose for little r and little h will impact the maximum volume of that cylinder because it's changing the cone that it's inscribed in. So that maximum volume should depend on both little r and little h, which is what we're seeing here. All right, we have 2 more examples that we're going to cover. This one right here. So let's read this. It says a company operates 16 oil wells in a designated area. Each pump on average produces 240 barrels of oil daily. The company can add more wells, but every added well reduces the average daily output by 8 barrels. How many wells should the company add to maximize daily production? So this is, again, something that you see a lot of in these optimization problems, this balancing act that I keep referring to. We have the potential to produce more barrels of oil by adding more wells, but the number of barrels each well produces will decrease as you add more wells. So we're probably going to see an increase in the production up to a point, and then if you add more barrels beyond that point, the production level of each well is going to be so low that it's going to probably cause a decrease in that production. So we're expecting to see a maximum value somewhere. First thing we need to do is come up with a function here, and I'm going to identify my variable. So W is going to represent the number of additional wells. We have to remember that there's already 16 wells there. So if I add one more well, then I'm going to have 17 wells. But W is not going to equal 17 in that case. It's only going to equal 1. It's how many additional wells I'm using. All right, so now what I want to do is try to come up with a function that we want to optimize. And the function should represent the daily production in number of barrels that however many wells we end up with will produce. So I'm going to call that f of w. It's a function of the number of wells. Now think about this for a moment. How do you determine the total number of barrels produced in a day? Well, it's the number of wells times the amount that each well is producing. We're assuming that each well is going to be producing the same amount of barrels each day. So number of wells times the number of barrels each well produces. So how many wells will we have? Well, it's going to be W plus 16. 16 wells that we're starting with plus however many wells we add on top of that. Now, if we add W wells to our set of wells here, how many barrels will each well be producing? Well, without adding anything, we know that there's 240 barrels being produced by each well each day, but then that decreases by 8 barrels for each well that we add in addition to the original 16. That would be minus 8W. Okay? So I'm going to simplify this a little bit. I can factor in 8 out of this, this guy right here, which would give me 8 times W plus 16 times 30 minus W. And normally I've been leaving things in factored form, but actually this time I'm going to multiply at least the parentheses out. This will give me 8 times negative W squared plus 14W plus 480. The only reason I'm doing that is because I know I need to take a derivative here, and I don't really want to bother with the product rule. So now, where is this function defined? Well, it's defined on the interval from 0 to, well, we could say infinity, I guess, but I think it's actually more accurate to say 0 to 30. And where am I getting that 30 from? Well, if I have 30 wells and I plug 30 in for W, then this is going to become 240 minus 240. It's going to go to 0. Basically, 30 additional wells is going to be the point at which the production level of each well drops to 0. Now, that's not really what would happen in reality, but if we take this as accurate information here, that's what it's telling us would happen. So really, this is a closed interval from 0 to 30, because we could also not add any wells at all. So we're going to use our closed interval method here. I need to find my derivative. F of W is equal to, F prime of W is equal to what? So I'm plugging in I'm not plugging anything in. I'm taking a derivative. I have an 8 there, and then this becomes negative 2W plus 14. And we're going to set that equal to 0 to find a critical number. Solving this would give me W equals 7. Okay? Now, that's in my interval here, but I should check my endpoints as well. So using our closed interval method, we know that the absolute maximum and absolute minimum values of our function have to occur at either a critical point or the endpoints of my closed interval. So we're plugging these into the original function. What is f of 0? If I plug 0 in for f, I'm going to get 8 times, these two terms go away. I just get 8 times 480 there. Okay? 8 times 480. Why am I blanking on that all of a sudden? We're going to do old school arithmetic here. This is what I should be able to do in my head. Embarrassed. 32, 38, 3,840. So we have 3,840 barrels that are going to be produced if we don't add any wells at all. If I plug in my other endpoint, 30, we already determined that that would give us 0, right? Because if I use this factored form right here, that's going to become 0. This is going to produce no oil at all. Then if we plug in f of 7 into our function, that's going to equal, I'll use this factored form, 8 times 7 plus 16 is 23. 30 minus 7 is also 23, so that becomes 23 squared. 8 times 23 squared is 4,232. So this is the largest number that I got using my closed interval method. That must mean that that's the maximum number of wells I can get. Okay, so the question didn't ask what the maximum was. It asked how many wells should I add to maximize that daily production? And the answer is 7 wells. Okay, so far so good. So we've got one more. This is going to be the most complicated one that we do, and that's why I saved it for last. So what we have here are two vertical poles, PQ and ST, and it says they're secured by this rope PRS as shown here. It says show that the shortest length of such a rope occurs when theta 1 is equal to theta 2. Okay, theta 1 and theta 2 are the angles that this rope forms with the ground. There's an angle here and an angle here that is referring to. Okay, so this is an interesting problem. We want to minimize the length of the rope, and we want to show that that occurs exactly when theta 1 is equal to theta 2. Now, there's a couple of additional labels I want to add to this diagram. So there's a couple of constants here. There's actually 3 constants in particular. The height of these poles is not changing based on how I position this rope. So the heights are constant, and I'm going to give them names. A and B are going to represent their lengths. Also, the distance between the poles is not changing either. So that is a constant as well. I'm going to call it D. Okay? Then I'm going to notice that these angles are appearing in 2 different right triangles. That's going to be useful. We have a lot of knowledge about right triangles that we can use. So what I'm going to do is take one of those right triangles and call its base x. Its length is going to be x. That would imply that the base of this other right triangle is d minus x, since these would add up to d, the total length from the total distance from one pole to the other. Bear in mind that a, b, and d are all constants. X is a variable, because if you notice, the way that we can get different lengths of rope here is by attaching the rope at different points along the ground, which would change x. Okay, would change the base of those right triangles. So now let's do a little bit of work with these things. By labeling a couple of sides in each of my right triangles, that allows me to use the Pythagorean Theorem. And the Pythagorean Theorem is going to be useful because the rope itself makes up the hypotenuses. I actually don't know if that's plural or not. The hypotenusi? I have no idea. Each hypotenuse, when added together, will give me the total length of that rope. So what I'm going to do is find the hypotenuse of each of these right triangles and add them up to get the length of my rope. I'm going to call that function L of x. Again, x is the only variable here. So what is the hypotenuse of this first right triangle? Well, it would be the square root of d minus x quantity squared plus a squared. That's just straight from the Pythagorean Theorem. The hypotenuse of this second right triangle is the square root of x squared plus b squared. Okay? So far, so good. Now, what we need to do here is take derivatives. The last example that we did involving the distance formula, which had a radical, we showed that you can eliminate the radical by only focusing on the radicand, and the function that you're maximizing or minimizing will give you this. You get the same result with that. That thing that I mentioned in that previous example does not apply here. So we actually do need to take the derivative of this. L prime of x. I'm going to need to use the chain rule here. And what you're going to get from the chain rule is negative 2 times d minus x. Now think about that. That's the derivative of this inside function here. A squared is a constant, so it goes away. Here I need to use the chain rule, and that negative is why that negative x in there is going to give me a negative 1 when I take the derivative of that inside function, whereas that's where that negative is coming from. Knowing what the derivative of a square root function is, I should end up with this down at the bottom. Okay, and I can do a little canceling there. Similarly, I want to take the square root of this guy up here. I'm going to get 2x over 2 times the square root of x squared plus b squared. Again, I'm using the chain rule. You should verify for yourself that that's what you would end up getting. I can cancel those 2's as well. Okay, and what I need to do is set this equal to 0. So what I'm left with on this side is negative d minus x over this radical function plus x over this radical function. So I'm going to take the negative 1 and add it to both sides. And that's going to give me this. X over the square root of x squared plus b equals d minus x over the square root of d minus x squared plus a squared. Okay? Now, it seems a little odd, or it seems a little tricky, like knowing where to go from here. Normally, what we would be doing is trying to solve for x, but you're not going to do that in this case. Because these two expressions here are on either side of this equal sign can be written in an entirely different way, and this is where we're going to bring these angles into the mix. So where does x show up in our diagram? It's the base of this right triangle. And what is, I forgot my second power there, what is the square root of x squared plus b squared? Well, it's the hypotenuse of that right triangle. So if I take the base of that right triangle, which is adjacent to the angle theta 2, and put it over the hypotenuse of that right triangle, that's the same thing as cosine of theta 2. So this left-hand side is cosine of theta 2. Okay? My right-hand side, if I look at that one, is equal to cosine of theta 1. Because again, I have d minus x, which is adjacent to side theta 1, over the square root of d minus x quantity squared plus a squared, which is the hypotenuse. I get cosine of theta 1 there. Okay? Now, the cosine function is not a one-to-one function normally, but if you think about this for a moment, we know that both theta 1 and theta 2 are acute angles because they are they're one of the two non-right angles that appear in a right triangle. And that would mean that if you think of these angles as being in the unit circle, they would belong to the first quadrant of the unit circle. And if you restrict the domain of the cosine function to the first quadrant of the unit circle, the cosine function is one-to-one on that domain restriction. What that means is that if you have cosine of theta 2 equals cosine of theta 1, and both of these angles are in the first quadrant, then those two angles have to be equal to each other. Theta 1 would have to equal theta 2. Okay? So that establishes what we're trying to show, that theta 1 is equal to theta 2, at the very least when the value that we plug in for x is a critical number of this guy. Now, notice I didn't find x explicitly. And we also didn't say whether this is going to give us a maximum or a minimum value. So the next thing I would want to do is try and verify if we're looking at a maximum or a minimum value. Remember, what we want is the shortest length of rope in this diagram, such that the rope is attached in this way. So how can we show that? Well, I don't know what x is, but is there any kind of restriction that I can put on x? There is, because again, remember, x is the distance from one of these poles to the rope. And the rope can be moved anywhere, getting close to the base of this guy or over to the base of this guy. So if I attach the rope, exactly vertically downward at the base here, I'd have 0 there. That's the smallest x can be. We're assuming that we can attach the rope to the base of this pole. We're also assuming that we're not going to attach it past the pole or anything like that. The largest it can be is d, because that would be stretching the rope the full length across and attaching it to this over here. Okay? So if I were to use, let's say, my first derivative test and plug in these two values, I know that my critical number, which I'm going to continue calling x, is in between 0 and d. And I'm just going to go ahead and use 0 and d as test points to see what happens on either side of x. So if I plug in 0, for example, we're plugging it into this derivative up here. If I plug a 0 in for x, I'm going to get 0 over the square root of b squared. That's just 0. And over here, I'm going to get d over this square root of, this would become d squared plus a squared. Okay, so this term goes to 0. This term becomes d over the square root of something. Now, d is positive because it represents a length or a distance. So that's a positive number over a number that would also be positive. Oh, yeah, but you know what? I'm forgetting that there's a negative out front. So it's actually negative d up on top. So negative number over a positive number, because you only get positives out of square roots. Non-negatives technically, but it wouldn't be 0. So that would be negative over positive, which is negative. That means L prime of x is going to be negative over here. And then if I go over here, I'm going to use d as a test point. If I plug d into my function, now I'm going to have d minus d up on top here, which is 0. over the square root of a squared. That's just going to go to 0. If I plug d in over here, I'm going to get d over the square root of d squared plus b squared. That's positive over positive in this case, which is positive. So L prime of x is going to be positive over there. That means we go from decreasing to increasing, which tells me that that is in fact a relative minimum. That's what we wanted. So that establishes what we were trying to prove, that if we find a value of x that is a critical number of this function, then it's going to be a relative minimum, and it's going to occur when theta 1 is equal to theta 2. This is a little bit different than the other optimization problems that we looked at, but like I said at the beginning of this lecture, these problems come in a big variety, and there's plenty more that we could talk about, but I'm going to leave that to the homework. So that's going to wrap up section 4.7.